Hello and welcome back to Differential Equations section 1.8, Acceleration Velocity Models. When we talked about separation of variables, we apply those to our equation that acceleration is acceleration of gravity, and then acceleration is change in velocity in time equals to gravity. You can actually use negative g, right, because it pulls down. Gravity is actually folding of space, but it manifests itself as this force that pulls on things. In hyperbolic geometry, space-time curved, and the straight line in that geometry is perceived to us as a pull down, which is gravity. So that all comes from the general theory of relativity, if you want to study that at all. But the easiest way for us to perceive it is what it is. But you have to understand that when you drop something and that something falls directly down, like a eraser, right? It's the same pull that moon is experiencing, and yet the moon is not crashing onto the surface of the earth. So the straight line that you experience when you drop something directly down and the motion of the moon around the planet, it's the same concept that propels both.
Well, is it also the same idea as the International Space Station?
Yep, all of it, all of it. So whatever is
there's horizontal.
What?
So
out. Get out. So those are the same concepts. So now we experience this as a pull down. And I'm just going to say the separation of variables over here. So dv equals negative g dt. Hit both sides with the integral, right? And we are getting our first velocity is equal to negative gt plus some constant c. And when you fix that, velocity in time is the initial velocity minus gt. You know this formula. I said that from physics, from kinematics. So motion as probably v final is equal to v initial plus acceleration times time. This is just another derivation of the same equation where that acceleration and gravity are the same thing. So this is if you're dropping the model, then over there is your car, for instance, right? When you push the gas pedal, you have the acceleration. So from this model, eventually you get that the position in time is negative 1/2 gt squared, right? This is the parabolic motion when you throw something, plus v0 t plus the, let's say, y0, initial height. And if you are, the difference between dropping objects and tossing objects is going to be in this term, because dropping an object, initial velocity is 0. Throwing an object is going to be the initial velocity that your arm had as you were throwing it. So those are some initial thoughts about acceleration and velocity, which we can derive directly from knowing that gravity is 9.81 meters per second, or 32.2 feet per second, depending on which units and system of units you want to use. So moving on to more immediate stuff, the force is ma, right? So force equals ma for the non-calculus based physics, but then we understand that acceleration is the derivative, right, of velocity. So it's a change in velocity. So we can write that the force is equal to mass times dv. dt, which again introduces a situation where we can integrate and do stuff. The free fall in ideal conditions, which in physics classes you always do the ideal condition, you drop an object and you don't consider air resistance, which is a problem, right? If I drop a rock and if I drop a paper, they are going to behave differently as they fall, because the paper will be really impacted by, right, or talk about the parachute, right? They will be really impacted with the air resistance, where the rock will not, right? Now, these objects are supposed to, in the vacuum, right, they're supposed to fall at the same rate. Now, obviously, the heavier object, right, will be getting down faster. However, the acceleration happens at the same rate because gravity is 9.81, whether you throw a feather or you throw an elephant. It's going to be the same acceleration, which is the rate at which speed is picked up. Now, you are going to consider, in this case, force due to gravity when you drop something. So mass times acceleration, which you're writing as dv dt, is going to be force due to gravity plus force due to air resistance. Now, the Fr, which is our force due to air resistance, is going to be proportional to the square of the speed at which you are going. So that should be somewhere in, oh, there it is. So Fr is equal to K, some constant of proportionality, and then V squared. So well, that's by Newton, but you can actually have any, let's put P, you can have any exponent in there. So now what's happening here? We are going to take, first of all, look into convention, the sign convention. We set up our x-axis positive towards the right. We set out our y-axis negative towards, right, going down. So the air resistance is going to oppose the motion. Therefore, the air resistance, the force of the air resistance should be always negative. Think about the Hooke's law as well for the spring. It's always negative values, should be negative. Force equals negative K delta X, because when you compress the spring, spring wants to push out. When you stretch the spring, spring wants to push in, right? So the force, whatever you do to the spring, the force of the, expressed through the Hooke's law, is trying to do the opposite thing. Rubber band does the same stuff. So now for the air resistance, when the object is falling down, air resistance, right, is the force that goes up. If you launch the rocket in vertically up, the air resistance is trying to push it down. So it's, yes? Well, I'm going to now write the Fr for the resistance proportional to the velocity is going to be taken as negative kV. Mathematics is not sensitive to this at all. It really doesn't matter in terms of mathematical derivation, but the physics is very picky regarding the reference frames. So we have to use negative sign if we are going to reflect physical reality. So mathematics doesn't care. Differential equations, they don't care whether you have a minus sign or not. But physics does. And if we want to use differential equations to model physics, we have to put that negative in there to match the reality of the 100%. So
Where our exponent go? Or P?
we are changing now to proportional to velocity, not velocity squared. So this is resistance proportional to velocity. So Newton said it's velocity squared, but then it depends on the shape of the object, and right, because right, if I drop the paper, it's going to take like longer time. Yes.
When I was looking at like the shape of the object, it only referred it to the cross-sectional
Area. Yes. Well, that's the shape of the object, right?
Yeah.
Cross-sectional area. You definitely don't want to jump without a parachute, right? Because your cross-sectional area is not going to be as
Well,
wide.
I can do that. I just need a huge net. They already did this.
Yeah, just let's not.
I just need a huge net.
And make sure I'm not jumping with you. So the total force is the force of resistance plus the force of gravity, which is negative kV for air resistance, and negative mg. G is negative, G is right going down. So if you are considering that, these guys are always in opposition to each other. Always in opposition to each other. Now we know that the force, right, this puppy over here, is mass times change in velocity or change time, which is the mass times acceleration, equals to negative kV minus mg. And hello, separable, right, differential equation, because we have variable v on both sides and variable t. The rest are all constant, right? Mass of the object that you drop, right, is constant. And, well, on this scale is constant. Remember that when you drop something from high up, the potential energy changes, E equals mc squared. So there is this really tiny change in mass. So mass is not constant, but we don't have to consider that change in what we are doing here, which is Newtonian physics. But if you are planning on satellites and GPS and stuff, you have to take effects of relativity in consideration. In this case, we don't have to worry about that. So we say mass is constant because that slight change, which are the fraction of a fraction of a fraction of a gram due to energy change, is not going to take this calculation and make it wrong. So we have m constant, k constant, g constant. We also know g is not constant either. If you have a huge drop, right, from the top of the Mount Everest and the bottom of the Mount Everest, there is a delta g there. 9.81 is the average change, and you would probably know more about the change in gravity. Yes, because it depends on your gravitational pull, depends on.
They actually did an experiment with not so much gravity but time, but they knew gravity affected the time.
Well, the gravity, the acceleration due to gravity is stronger, right? Because the force due to gravity falls off with the square of the distance, right? It's g times mass of the one times mass of the other divided by the distance squared. So those effects, again, are, for our experiment, negligible, because on the surface of the planet, we just average that to 9.81 and can keep it there. So if you are looking at this equation, this is a differential equation that only has v as a variable, which is a velocity that changes because of acceleration, because of gravity, and you also have time, which flows, right? So now, to solve this differential equation, you can divide through by m to get dv dt alone. So I'm going to divide through by m everywhere, and we're going to have dv dt alone On the other side, I have negative k over m times v minus g. And as I see in the textbook, they take the rho k over m, so Greek letter rho, to replace k over m, so we have less. Well, it's going to be negative in the equation. Okay. So dv over dt is negative rho v minus g. And there you go. You have the separable differential equation. All of this is now one unit. It goes under dv. And we have the separated equation, negative rho v minus g equal to dt. We integrate both sides, and we use u sub to solve this problem by defining u to be negative rho v minus g. Du would be just negative rho dt, sorry, dv. There we go. And by plugging everything in and working this out, you are going to get the ln of negative rho you have to have a negative, which you can factor out of here, and then, yeah, so it's 1 over rho v plus g, right? Yeah, I don't like these minus signs, so what I'm going to do is I'm going to pull out the minus sign here and have dv over rho v plus g, right, equals to t plus c on the right hand side. I'm going to change all of these minus signs here into plus signs, so I have a minus in front, and that gives the whole thing much better vibe. There we go, equals to t plus c. Now this negative can go to the other side of the equation. All right, becomes negative t plus c. So ln rho v plus g equals to negative t plus c, at which point we e both sides, and we have rho v plus g is equal to e to the negative t, and then e to the c. We can have a constant for that. Obviously, we're going to use v0 because that's our initial condition. So just trying to see if we are going to use the v0 now. You know what, let me call it capital B again, and then we'll figure out. So what I need now is to subtract g on both sides, divide by rho. So v of t, which is the velocity, is going to be b e to the negative t minus g, everything divided by rho. And yeah. Why did it say rho t? Did I miss something?
Yeah, that didn't make any sense.
Oh yeah, I forgot the rho. Yeah, I'm trying to figure out where did I lose rho. So yeah, this rho from u sub, it's gonna pop up here. Yeah, I was trying to figure out what's off because I didn't like the. So there's the rho t. There we go. So it's 1 over rho on the left or times rho on the right, which is better. All right, much better. Whew. All right, so now this b is going to be our initial velocity, and we have exactly what we what we need. So v of t, when you factor everything out, becomes v0 plus g over rho e to the negative rho t minus g over rho. Yes.
Rho, we said is
Rho, yes.
Yeah.
So rho is k over m.
K over M. So we don't know what K is, though, right? We can figure it out, though.
K is a constant of, yeah. So now this is the equation. And what we want to do now is take a look at something that's called terminal velocity. So,
I know all that.
So if you never had physics, you're behind in this, or it's okay? You never seen it?
I mean,
this in-
no, this
you
is
wouldn't really
this is
learn
actually the beginning of the stuff.
Okay.
So when you throw something and starts falling, it will always be accelerating due to gravity, which exerts the pull. But at some point, the air resistance will equal the force of gravity, and at that point, the object will stop accelerating. The object will be falling at the constant speed, and we call that terminal velocity. So let me draw, I will erase this, but let me draw the diagram here. So say I am throwing this rock. For this part of the trip, that rock is constantly pulled back by the air resistance, but the force due to gravity is much higher, so the rock is experiencing acceleration. And then at some point in time, right, in this fall, the rock is going to have equal amount of pull and push. So this is your Fg, and this guy over here would be Fr. And those two vectors would be the same quantity. Now remember that the object already had velocity, and that velocity we call velocity tau, velocity terminal, right? Tau is the Greek replacement equivalent of t, right? So that tau is what we call terminal velocity. Now, the terminal velocity happens when the force of gravity pulling down and the air resistance opposing it, when those two forces are equal. At that point, the object will no longer accelerate. So below this line, acceleration equals 0. We still have velocity. The object is moving. And it's now, we say, moving at terminal velocity. So velocity in this part of the flight of the rock is constantly changing. It's constantly increasing because the gravity is pulling rock faster and faster and faster and faster, until the moment where the terminal velocity is reached, and at that point the object is no longer accelerating, is now falling at the constant rate, constant speed.
What's the arrow shooting up next to F?
Well, that's the FR,
That's
that's the resistance, the resistance, yes.
So it'd be air molecule.
Air molecule.
All right. Well, we have plenty of time. And the terminal velocity, the terminal speed, you guys are going to obtain that from this equation, again, taking the limit. Remember what I said? You keep taking the limit, and you get stuff for differential equations. So in this case, limit t goes to infinity, right? Let it fall to infinite time. So of v of t, and when you consider that, right, it will kill this term because it would make it a 0, and you are left with g over rho. So it would be negative g over rho. And then we know that rho, right, was defined as k over m. So the terminal velocity, well, terminal speed, right, would be the absolute value of negative g divided by k over m, which actually works out to be just mg over k. And this one over here is what we call terminal speed.
The whole thing is terminal speed?
Well, just the equation mg over k is the terminal speed, right?
Do you care about pressure and density?
Not yet.
Okay.
Now you get to redo this calculation for a square, which is done next, resistance proportional to the square of velocity. Then you can come up with a cube and everything else. And the one that is really interesting, guys, and you should really look into it if you want to work on your rocket propulsion, is going to be the page 92. So look in this one. It's called escape velocity. Just give me a second here. So escape velocity, you heard before the really silly statement which says what goes up must come down.
Unless it's going
Hell no.
7 miles a second.
Whatever you shoot up with a greater speed at 7 miles per second is not going to come down, because the escape velocity of planet Earth is 7 miles per second. If you can accelerate anything with that speed, it will escape Earth's gravitational pull, and that is called escape velocity. Now, the equation for the escape velocity can be easily calculated here. You have the derivation in the book. Again, it's just a formula that you plug numbers in. So just look at the escape velocity because it's related to the rocket problem, page 95, which is project 1 out of the, so it's one of the two choices that you can, right? You can either do the chicken or the turkey or whatever baking you want to do, or the rocket. See you all in 5 days, or sooner.
Look at this.
Give me a second to just